All right, welcome everyone to this first video in our discussion of chemical equilibrium. And in this video here, we're going to just kind of present the idea of what is chemical equilibrium, what does that mean when we talk about it. So let's consider a reaction that reaches chemical equilibrium, right? So in my reaction here, I have NO2 forming N2O4. Okay, so in my initial stage of the reaction, right, so this is like T equals 0 here, my initial stage, right, I got a bunch of NO2 molecules. Okay, as the reaction goes, right, some of these NO2 molecules form N2O4, and then you reach a point where now I have, say, 1, 2, 3 N2O4s, and then I have 1, 2, 3, 4 NO2s. Okay. And as time goes on, right, I will still have, once this reaction's reached equilibrium, as time goes on, I'm still going to have 3 N2O4s, and I'll still have 4 NO2s. But you see, right, one of the things is that the molecule, the atoms that make up the N2O4s, the atoms that make up the NO2s, right, have changed over this time, right? And so what's happening here, right, is what we'll be talking about in this video, right, is the idea that this reaction hasn't stopped from step C to step D here, right, at time T equals C and then time T equals D, right? The reaction is still going, but the reaction's occurring in such a way that the concentration, the amount of reactants and products isn't changing, okay? Right, so as we'll see, right, as we continue talking about this, from kind of this line to the right, in step C, D, we've reached equilibrium. Okay, right, before that we're not in equilibrium, after that we do reach equilibrium, right? And if you look at this, say reaction taking place, right, N2O4 is a clear gas, while NO2 is a brown gas, right? And so you reach a point where you reach some steady equilibrium where you'll have some N2O4 and some NO2 existing in this container on the right, right? You see here N2O4s, some NO2s, right? The concentration of those things will be steady once this has reached equilibrium. Okay. And so how can we kind of look at that, right? So we can look at concentration versus time of our reactants and products, right? See here, in this case, the reactant is N2O4 and the product is NO2, right? So if I write my reaction N2O4, I'm going to 2NO2, right? And so what we see, right, at time 0, right, there's no products, it's just reactants, okay? And as time goes, we reach a point, right, with this dashed line, where I reach a point where now the concentrations N2O4 and NO2 are constant, okay? So once the concentrations are no longer changing, we say we've reached and achieved equilibrium. But if you look at the rate of the reactions, right? So my reaction here, okay, right, was N2O4 going to 2NO2, right? Well, that is the reaction in the forward direction. The reaction can also go in the reverse direction, NO2 going to N2O4, right? Well, the rates of these two different reactions, right? So if I'll label this reaction 1 and this reaction 2, okay? Reaction 1 has a rate of just the forward reaction, Kf, so the forward reaction rate constant times concentration of O2, right? So this is the rate of reaction 1. And this is the rate of reaction 2, right? Initially, that rate is 0 because initially I don't have any NO2 in this reaction. Okay. But as the reaction goes, right, I build up concentration of NO2s, those NO2s will bounce around and potentially react with each other to form N2O4. Okay, and so there's some rate in which those NO2s hit each other to form N2O4, but then N2O4 is still continuing to decompose into NO2. And so I reach a point at equilibrium where the rate of reaction 1 is equal to the rate of reaction 2. Okay, so what's happening, right, when I reach chemical equilibrium, right, the rate in which my reactants are forming products is the same rate in which my products are forming reactants, right? So I'm forming NO2 just as fast as I'm forming N2O4, so that even though these reactions are still happening, they're happening at the same rate, so the concentration of reactant products are steady, they're constant, they don't change, right? Because I'm forming, you know, in the forward direction, I'm forming 2 NO2s per second, but in the reverse direction, I'm consuming 2 NO2s per second, right? So in the end, those cancel each other out, right? And I'm left with a steady concentration of NO2 as this reaction keeps going, okay? Now, every chemical reaction reaches equilibrium in this way, okay? Every single chemical reaction you could technically think of as an equilibrium reaction. Now, some reactions, right, the reverse direction is so slow that we just don't even consider it, right? We don't even count it because it's just so slow that it doesn't matter, okay? That you really won't reach a type of equilibrium. But technically, every reaction can go in the forward direction and the reverse direction, right? Just some reactions, that reverse direction might be extremely slow and unlikely to occur, and so we just consider the reaction to be unidirectional, right? Just to go in the forward rate, right? And that's what we've talked about so far in chemistry, general chemistry, the first semester. In the second semester, so far, all we've talked about is just a reaction going in one direction, right? Those reactions we've talked about, right, are reactions where the reverse direction potentially is so slow that we just ignore it. Okay, but every reaction technically can go in either direction, okay, and equilibrium reactions that reach equilibrium, right, those reactions, that reverse direction is fast, and is fast compared to the forward direction. Right, so kind of a sum of those last two slides, right, we see when we reach equilibrium, our concentrations stay steady, but our reactions are still occurring, they're just occurring at the same rate. So that is kind of what chemical equilibrium is. Chemical equilibrium is a dynamic equilibrium. It's a dynamic because things are changing, but it's an equilibrium because we have the concentrations remaining constant, right? So it's dynamic because those forward and reverse reactions keep occurring. Reactions are still happening once you reach equilibrium, but it's at equilibrium and things are staying constant in terms of the concentrations of the reactants and products remain constant, okay? So again, reactions are still occurring, just the overall change in concentration doesn't occur when you've reached equilibrium, okay? Right? And think of, right, you have some sort of, you know, sink, if you will, that's filled up, right, at some level, call it its equilibrium level, right, and you're pouring water into the sink through, say, the faucet, but then you open the drain to the sink as well, right? So water is draining out of the sink, but you're also pouring water back into the sink. If you drain out the water and pour it in at the same rate, the height of your sink is unchanged, right? The height of that water doesn't change, right? And that's what's happening in chemical equilibrium, right? I have reactants being formed, and reactions being consumed, and products being formed, and products being consumed, all at the same rates, right? So that the net concentration of all my reactants and all my products is unchanged once I've reached equilibrium.